nanohub.org.
So, in terms of summarizing the last lecture, the really important result that we obtained after this long discussion about electrostatics and how molecules interact, we finally came to the conclusion that there were three forces or three interaction energies that varied as 1 over r to the 6th. Right, so that's a common factor in all three of these, the Keesom, the Debye, and the London interaction energies. The Keesom interaction basically is a dipole-dipole thermal averaged interaction between molecules or atoms that have dipole moments. This Debye force is also an angle averaged interaction. But in the case of the Debye force, one of the dipole moments is induced, right, by something else. By, let's say, the electric field produced by a first dipole induces a dipole in the second atom or molecule. And then you have to do this weighted thermal average using Boltzmann statistics. And when you do that, you get the second term in this expression for the van der Waals forces. The third term is purely quantum mechanical, and the way you can pick that out is it involves ionization energies, I1, I2, of the molecules or atoms that are interacting one with respect to another. And the only way you can get the only way you can understand those ionization energies is from a quantum mechanical discussion of the electron states of an atom or a molecule. So the third term, the London term, is universal. It acts between all atoms and molecules, right? And it's purely quantum mechanical in nature. And I think it's customary in the literature to group these three terms together into one, and that grouping is represented as minus c, some constant, divided by r to the 6th. Okay? So what we tried to do is, in deriving this van der Waals, we didn't derive it, we tried to make it plausible, right? What we tried to do is we tried to systematically work our way through a variety of different electrostatic interactions. And we started with the strongest electrostatic interaction. That's the interaction between point charges. But unfortunately, or fortunately, most materials don't have point charges, so you have to consider second, third order effects. And so as you work your way down on this table, right, you're going from this point charge ion-ion electrostatic interaction to these much weaker, much shorter range interactions that involve interactions between dipoles of different atoms and different molecules. Okay? Now, one issue is how big, what's the representative sizes between the Keesom, the Debye, and the London terms, right? That's a fair question. The third term, the London force, that interacts between all atoms and molecules. That's independent of whether an atom or a molecule has a dipole moment. The other two rely on dipole moments or dipole moments that are induced by electric fields. And so, there have been a number of calculations done. I just pulled, I found one set of calculations on the web that illustrate this point. These coefficients that multiply the 1 over r to the 6th term for each of the three interactions, the Keesom, the Debye, and the London, those constants are evaluated on this page, on this slide for a variety of different atoms and molecules. And what you can see is that the contribution due to the London interaction, that's always there. It's independent of what substance you're doing a calculation for. The Keesom and the Debye contributions start to depend on the details of the atom or molecule you're dealing with. So, for instance, in the case of let's say water, right, the Keesom interaction is actually bigger than the London interaction, but that's because water has a strong permanent dipole moment. You would expect that. But these other entities like oxygen, nitrogen, the dipole moment is essentially zero, right? And so this Keesom and Debye interaction are negligible, they're zero. And what you're left with is just with this London. So this is the justification for saying that this London interaction is responsible for the interaction energy of these different, it's always there, right? It's always there. The other two depend on situations, and you have to evaluate. I tried to put together a flowchart diagram which indicates what we talked about in the last lecture. And so to the best of my ability, this is what I think I tried to say. If you like to read flowcharts, this might add some systematics to the discussion. But basically, it's saying that if you have a system of interacting atoms or molecules and or ions, right, you basically have to make two decisions, right? One decision is whether or not ions are involved. If ions are involved, you've got a possibility of a yes or a no. And then if yes, ions are involved, then you go through one branch of argument. If ions are not involved, you go through a completely separate branch, right? The other fundamental question is whether these interacting atoms or molecules, whether they are immersed in a material that has a dielectric constant epsilon, right? So you have to make a decision also up front whether you're using epsilon naught or whether you're using epsilon times epsilon naught in all these force equations. If you're dealing with two atoms or molecules interacting in air or vacuum, then epsilon, the dielectric constant, is very close to unity in air. It's defined to be unity in vacuum. Then you're just left with the epsilon naught factor in all those equations. But at the end of the day, right, you're left with these three interactions, which I've got enclosed in this box, and these are the three interactions that we generically lump together and call van der Waals forces. And these forces govern the attractive and repulsive interactions between electrically neutral objects, right? And of course, this is what gives rise to the attractive interactions of the tip with the substrate, right? How does this problem sort itself out in terms of atomic force microscopy? I try to illustrate that in this case, in this slide. This is a schematic slide. So you can imagine a uncharged sphere of radius r. This uncharged sphere is an approximation to an AFM tip, right? That uncharged sphere is suspended above an uncharged insulating plate. And the question is there any interaction force between the sphere and the plate? And to a first approximation, you would say, no, there's no interaction because the sphere and the plate are uncharged. There's no electrostatics. But it's possible, if you've understood this discussion of van der Waals forces, it's possible to realize that a molecule or atom in the tip, which has a dipole moment that's either permanent or induced, can interact with another atom or molecule in the insulating plate, right? And in the process of interacting, right, you've got all these van der Waals forces that you have to take into account, right? And so basically what's going on is the fluctuating dipole of the atom or molecule in the tip is interacting with the fluctuating dipole in the substrate, and if these interactions are correlated and can be added up according to the van der Waals forces, there could be a net interaction, a net attractive interaction between those atoms and molecules. So then what you'd have to do is you'd have to sum up those interactions. You'd have to use calculus to integrate the interaction over the entire region of interest, and we'll do that in the next lecture. We'll show how the integration can be performed for some simple geometries. So this van der Waals interaction is really an electrodynamic effect, and it's pretty subtle, but it's always there. And it's attractive. If you're in air, if the intervening medium between the tip and the substrate is air, this is always an attractive force. Okay? How big is it? Well, that depends. Right? That depends. It depends on something called the Hamacher constant. We'll talk about that more. But I just thought it would be useful to do a simple calculation where I take a sphere of radius r. In this case, I picked 10 nanometers, and I just put 8 electrons in that sphere. I pretended the electrons were uniformly distributed over the surface of the sphere. And I let that sphere interact with an uncharged plate, and the separation between the bottom of the sphere and the uncharged plate is d, so the surface to surface separation is d. And I just calculated the attractive forces that exist for the case of the charged sphere interacting with a metal or a dielectric plate, right? Those are indicated by the dashed red and the blue curves on this slide. And you can see that if there's net charges involved, this interaction force is very long range. It goes over hundreds or certainly tens of nanometers, right? Certainly goes over tens of nanometers. But if you take into account the van der Waals forces, okay, now you pretend that there's no charge on the sphere. You make the charge on the sphere electrically neutral, right? And then you ask how this van der Waals force varies as a function of the surface-to-surface separation. You end up with this black line on the far left of this view graph, right? So the van der Waals forces are essentially zero until you start to get within about 5 nanometers separation. And then they start to kick in and they rapidly increase, right? They rapidly go up, and then when the separation between the sphere and the plate is small enough, these van der Waals forces actually can be greater than the electrostatic forces that we calculated in the first step of this problem. Now, one thing you got to realize is that these van der Waals forces always cut off at some distance, and that distance is referred to as A naught in the literature. It's indicated by this little red tick mark, right? This distance A naught is basically the separation between atoms in solids. It's the lattice constant, right? And the argument is you cannot push 2 atoms closer together than this parameter A naught. If you refer back to the slides I did on the 612, on the discussion, if you refer back to the discussion of the 612 Leonard-Jones potential, the minimum interaction energy was specified at a position R star, right? That R star is equivalent to this parameter A0. It's a cutoff parameter. It just is telling people that you cannot get 2 solids closer than the inter-atom spacing. It's a number on the order of 0.2 to 0.3 nanometers, okay? And so van der Waals theory doesn't apply less than A naught, right? It doesn't make sense. Van der Waals theory also does not apply if you have, it's not, let me say, van der Waals theory is not so simple to apply if you have rough spheres or rough substrates. All of these calculations assume very smooth spheres, very smooth substrates. But at the atomic level, it's clearly not the case, right? There will be atoms protruding above the surface of the plate. There will be atoms protruding above the surface of the sphere, and these atoms will cause deviations, right? It's surface roughness issues, right? So this is kind of an ideal discussion, but it nonetheless gives the idea that this van der Waals can be very large, or can be significant. It can be significant if the separation between 2 things is small enough. Okay? So, what are the implications of all this discussion for atomic force microscopy? Okay, in AFM, we like to believe that the tip is electrically neutral. We like to believe that the substrate is electrically neutral. But tips are made out of silicon, and silicon has an oxide layer on it. So there's an SiO2 oxide layer on your silicon tip. It is possible that you can trap charge in that Si2 layer. right, in that oxide layer. Even though the bulk of the silicon tip could be mildly conducting, right? It could be doped to make it mildly conducting. The oxide layer that forms on the surface of the tip is not, and trap charges can exist there. Similar thing can be said for substrates, right? You could, principle, you know, you have to worry about a substrate with no trap charge on it, right? And then the other problem that happens is the tip interacts with the substrate. The tip can accumulate stuff, right? The substrate is always covered with a layer of adsorbates. And in the process of scanning, you can transfer these adsorbates from the substrate to the tip. It's possible that those adsorbates can transfer charge, right? They can carry charge from the substrate to the tip. So it wouldn't be surprising if you start scanning in the morning with the tip and your scans look good, and then as the day progresses, as the tip gets more contaminated, your scans start to degrade because of these electrostatic forces between tip and substrate that, in principle, we like to eliminate, right? Those forces are long range. If they're long range forces, then you have a very hard time getting contrast, you know, at the atomic length scale, which is one of the things that AFM is capable of doing, right? So you have to worry about that. The reason it's important, okay, the reason it's important is because these potentials scale, these 1 over R, the ion-ion, the 1 over R squared ion dipole, and the dipole-dipole is a 1 over R cubed interaction potential. Those are long range compared to this 1 over R to the 6th, right? So to do good AFM, you always want to have a van der Waals interaction between the tip and the substrate, because that's extremely short range. The forces that you're measuring are truly just the forces between the tip and the substrate at a very local level. If these electrostatics come in, then it gets more complicated. And in reality, of course, the attractive forces between the tip and the substrate, it's a combination of van der Waals and chemical bonding. You always got to keep that in mind, right? We haven't talked so much about the chemical bonding, the covalent forces between atoms in the tip and atom in the substrate, but in principle, that effect is always there, right? And so you have to think about it a little bit. So I think that ends the lecture. I want to skip on now to the next lecture where we take these van der Waals forces that we're going to approximate by this minus constant over R to the 6th. That's going to be our model for van der Waals forces. And we're going to start to now integrate those forces over geometries of tips and substrates to find out what the net interaction force is between the tip and the substrate. So that's the next item on the agenda.